Picture an office worker facing a deadline. Suddenly, an urgent email pops up. The body reacts. Heart rate variability drops, and skin conductance spikes as sweat glands activate. We capture these precise biological changes using wearable ECG and EDA sensors. This chart shows the two-dimensional psychological model of emotion. To accurately classify our subject's reaction as stress, their physiological data needs to plot directly into the top left quadrant, requiring a state of both high arousal and negative valence. To get from a racing heartbeat to a reliable prediction, we use a deep learning pipeline with 4 distinct steps. We extract the frequency domains from the raw signals, pass them through a joint autoencoder, feed that data into a CRNN-SE classifier, and output a binary stress prediction of 0 or 1. Predicting stress requires engineering and architecture capable of translating highly chaotic biological time series data into a definitive mathematical classification. Our first technical step isolates specific physiological rhythms from the raw waves using power spectral density. We transform the signals into the frequency domain, filtering the ECG wave into 3 distinct frequency buckets and the EDA wave into 5. This extraction isolates the most discriminative markers, yielding exactly 51 specific features from the cardiac data and 40 features from the electrodermal data. Because a heart rate and a sweat response operate on completely different scales, we merge these 2 arrays into a single combined input vector to feed into a joint modality auto. By compressing the data through 3 narrow hidden layers and calculating reconstruction loss, the model learns the underlying mathematical relationships between the 2 inputs. The autoencoder harmonizes 2 entirely different biological systems, cardiac and electrodermal, into one unified mathematical language that our classifier can process. Here is where many standard pipelines fail. If we feed the flat 2-dimensional arrays generated by the autoencoder directly into a recurrent network, the model fails completely. Recurrent networks require temporal context, so we reshape our data into a 3-dimensional cube tracking samples, time steps, and features. To capture how the subject's biological state changes over time, we apply a sliding window technique. A fixed frame, say a 5-second window, slides across the data, giving the neural network a sequence of events rather than a single frozen snapshot. We process this sequence with a 1D convolutional layer to identify immediate local patterns. The output from that CNN then feeds into a squeeze and excitation block. The SE block acts as a smart volume knob. It uses global average pooling to squeeze spatial information down, turning up the volume on the pathways that strongly indicate stress, while muting the irrelevant biological noise. With the feature selected, the data enters an LSTM layer. If we zoom inside an LSTM cell, we see a system of gates deciding exactly what temporal data to keep. This manages both the short-term spikes and the slowly compounding long-term stress states. The forget gate actively discards obsolete baseline data. If our subject was completely relaxed 10 minutes ago, the network learns to close the valve and drop that old information so it doesn't skew the current calculation. Meanwhile, the central cell state retains the slowly building baseline of sustained time pressure. When a sudden anomaly occurs, like an urgent, demanding email, the input gate opens to capture that immediate biological spike and mix it into the long-term stream. Pause the video. If our subject just received a stressful email interruption, which LSTM gate is primarily responsible for deciding whether to add this new physiological spike into the cell's long-term memory? It's the input gate. By layering a CNN for pattern matching, an SE block for noise filtering, and an LSTM for complex memory management, we engineered an architecture that mirrors exactly how the human body processes environmental stress over time. In the final step, the complex temporal output stream from the LSTM feeds into a dense layer, and the result is squeezed through a sigmoid activation function to map the value between 0 and 1. The function outputs a final probability score of 0.89. Because we built the model against our initial psychological baseline, this high score explicitly maps to the high arousal and low valence quadrant, confirming a definitive state of stress. Here is a comprehensive view of the entire system architecture. Save this structure for your own biological deep learning projects. Extract power spectral density, run the joint autoencoder, reshape with a sliding window, and classify with the CRNN-SE. You've successfully traced the pipeline from raw, noisy heartbeats and sweat down to a highly optimized multimodal predictive model.